So the way we can reconstruct temperatures back over the Pleistocene in the ice core comes from different isotopes of oxygen. It turns out that the person who discovered this was the same guy who did this important work in ice cores, Willy Dansgaard. In the 60s, Willy Dansgaard published a paper where he observed how the ratio of oxygen 18 to 16 in precipitation all over the world varied with mean annual air temperature. And it's really quite remarkable. The data he measured plots beautifully on a line. If you plot mean annual temperature against the delta 18 of precipitation, it's almost a perfect line. It turns out that at very warm temperatures in the tropics, this falls apart for a variety of reasons now that are pretty well understood. So this temperature delta 18 relationship breaks down at warm temperatures. Luckily, there aren't too many ice cores that form at very warm temperatures. So we're mostly okay with this, using this as a thermometer. And this is the basis for reconstructing temperature from these ice cores. Now, the way we do this is using isotopes of oxygen. Now, as we know, all oxygen has 8 protons in the nucleus. And in general, most oxygen has also 8 neutrons. And that is a mass of 16. But some oxygen has 8 protons and 9 neutrons. And that would be mass 17. And finally, other atoms of oxygen have 8 protons and 10 neutrons. And that would be mass 18. Now, all of these atoms are oxygen atoms because it's the protons that define what element this is. They all behave chemically the same. They all have 8 electrons. The only difference is the number of neutrons and therefore their mass. And so chemically they behave very similarly except for some very subtle differences that depend on mass. Now, in terms of their abundance, as I said, the vast majority of oxygen is oxygen 16. In fact, about 99.76% of all oxygen is oxygen 16. And then we write it this way with a 16 before the O. Oxygen 17 is very rare. It's about 0.04%. And oxygen 18 is slightly more abundant, about 0.2%. So as you can see, most oxygen is oxygen 16. A very small amount are these heavier isotopes. All 3 of these nuclei are stable. That is, they don't radioactively decay. They just behave slightly differently because of the different masses. So let's think about how these different isotopes of oxygen actually behave in nature. Let's first take a simple molecule like a water molecule that is H2O. Now, what I'm going to do here is I'm going to write the mass to the left here, and I'm going to write the number of protons down on the bottom here. Just to remind you that, of course, hydrogen is 1, and it has no neutrons. It has just a proton. And so it's mass 1 and 1 proton. In this case, we'll write the oxygen as mass 16 and 8 protons. So here's a simple water molecule. If we draw another one that looks almost identical, also with 2 hydrogens, but instead with a oxygen 18 atom on it, as I said, these 2 molecules behave very, very similarly. It turns out, though, that there's a very small difference between them, which is that the molecule that has the heavier isotope of oxygen, that these bonds between the hydrogen and the oxygen are slightly more stable with a heavier atom. These extra 2 neutrons make this bond just a little bit stronger. And so as a result, there's a slight preference that all water molecules have for this oxygen 18. So these two molecules would be all mixed up in a liquid water, for example. But when you have two different phases, like liquid water and water vapor, things get a little more interesting. It turns out there's a competition within the water molecules between oxygen 18 and oxygen 16. As I said, all molecules would prefer to have a little bit more oxygen 18 because these bonds are a little bit stronger. What we're going to do now is write a simple oxygen isotope exchange reaction to describe what happens when there's two phases, like water liquid and water vapor, when water is, say, evaporating from the ocean. We can write it like this. So we have H2O18 in the liquid plus H2O16 in the vapor. And that goes to H2O18 in the vapor plus H2O16 in the liquid. You can see in this isotope exchange reaction, not much is happening here. All that's happening is you're exchanging the oxygen 18 in the liquid for an oxygen 18 in the water vapor. So all that's happening here is that oxygen 18 atom is switching allegiances between the liquid and the vapor. We can write an equilibrium constant for this reaction. What happens when this reaction comes into equilibrium so that the forward and backward reactions or rates are the same. And in that case, that equilibrium constant is just equal to the product of the products divided by the product of the reactants. And that's very simply oxygen H2O18 in the vapor times H2O16 in the liquid divided by H2O16 in the vapor times H2O18 in the liquid. Now, we can rearrange this to make this just a little bit simpler for us using some very simple arithmetic, just essentially moving the liquid terms into the denominator and moving the vapor terms up into the numerator. This is simply the ratio of H2O18 in the vapor divided by H2O16 in the vapor divided by H2O18 in the liquid over the H2O16 in the liquid. So this is just the ratio of oxygen 18 to 16 in the vapor phase versus the liquid phase. If you were to measure that value in the laboratory, that would be approximately 0.99. What that actually means is that at equilibrium, there's a slight preference for oxygen 18 in the liquid phase relative to the vapor phase, or about a 1% difference. So there's at equilibrium, 1% more oxygen 18 exists in the liquid than it does in the vapor. So let's apply what we've learned now to the system of water vapor evaporating from the ocean. We can draw the surface of the ocean here, and the delta O18 of the water in the ocean is going to be approximately 0 parts per thousand, or 0 per mil. We write per mil as a percent sign with an extra 0 here. It's 0 per mil because one of the standards we use is called standard mean ocean water. And so therefore, using that standard, by definition, seawater is very close to 0 per mil. So when water evaporates from the ocean into a cloud, If you recall that equilibrium constant of 0.99, what that means is that the liquid water is about 10 per mil enriched relative to the water vapor. So that means that the delta O18 of the cloud is going to be approximately minus 10 per mil relative to the ocean. So we have a cloud with water vapor at minus 10 per mil and the ocean at 0 per mil. Now, let's imagine what happens when that cloud moves over a little bit and now rains out over, instead of the ocean now, let's imagine that it's raining over a little bit of land. The first rain that falls from this cloud, remember the delta O18 of the cloud is approximately minus 10 per mil. And the first rain that falls, these are liquid water droplets that form out, assuming there's no change in the temperature, and that's a simplification we'll make here, because there is a small effect of temperature here. Then the delta O18 of the raindrops is simply going to have that same fractionation, that same preference for oxygen 18, and the delta O18 of the rain will simply be 0 per mil. But now think about what happens to the cloud. The cloud is minus 10 per mil, and it's losing water that's slightly enriched in oxygen 18 at 0 per mil. And therefore, what happens is, if you say lost 10% of the water, that cloud is no longer minus 10 per mil. It's lost a little bit of extra oxygen 18, and therefore, the cloud now evolves to becoming slightly more depleted. So the delta O18 of this cloud now is approximately minus 11 per mil, getting a little bit depleted. Now you can imagine what happens as this continues. You keep losing rain. In this case, the rain from this cloud would no longer be 0 per mil. Now the delta O18 here would be minus 1 per mil. And if you lost another 10%, the cloud would get lighter and lighter and lighter. We call this process Raleigh distillation. And when the cloud starts losing a very large fraction, imagine that it's losing 90, 95, even 99% of the water in the cloud, what happens is that the delta O18 of the residual vapor in the cloud gets more and more depleted, and the delta O18 drops to more and more negative values. We can describe this process with a simple graph that actually looks at the delta O18 of the water as a function of the fraction of water in the cloud. And we can think of that as going from 1 to 0. So think about the original cloud. If we plot the cloud here, this would be minus 10 per mil. Remember then that the seawater would be up here at about 0 per mil. So here is the original seawater, and here is the original cloud. As the rain falls, as we said, the delta O18 of the cloud is going to become slightly more depleted, and the rain is always going to be about 10 parts per thousand, or 10 per mil, enriched relative to that water vapor in the cloud. And so there's always going to be about a 10 per mil difference between these two lines. As the fraction of water in the cloud gets less and less, it turns out that the depletion of oxygen 18 gets greater and greater. So by the time you're down to a very low fraction of water vapor remaining in the cloud, this can be minus 50 or minus 60 parts per thousand. And the rainwater that falls will similarly be very, very depleted. It looks like these two lines are converging, but in fact, the difference is always 10 parts per mil. We can describe this change in the isotopic composition of the cloud with time using a very simple equation for Raleigh distillation, just the ratio of oxygen 18 to 16 in the cloud divided by the initial ratio of what that cloud was when it started is just equal to that fraction remaining, that F, or how much water is remaining in the cloud, raised to the alpha minus 1, where alpha, this is that equilibrium constant for that isotope exchange reaction. So essentially, as the fraction of water remaining gets smaller and smaller, this term gets more and more depleted. So this explains this remarkable curve that Willy Dansgaard saw when he plotted the delta 18 of precipitation against mean annual temperature. What he was seeing was essentially the change in the amount of water vapor in the atmosphere, which is a very strong function of temperature. As a cloud evaporates at low latitudes and then moves, as the air mass moves towards higher and higher latitudes and the temperature drops, the amount of water remaining in the atmosphere gets lower and lower. So you can think about the process of water evaporating near the equator and moving towards higher latitudes as a process of distillation. As the water in the atmosphere drops out as rain and ultimately as snow, the water vapor remaining in the atmosphere as clouds gets more and more isotopically depleted following this simple Rayleigh distillation model. And by the time you get snow falling in the middle of Antarctica, the delta 18 of that snow is extremely isotopically depleted and is a very strong function, as Dansgaard showed, of the mean annual temperature. For the Antarctic ice cores, actually the scientists didn't measure the delta 18. What they actually measured was something a little different called the delta D. And this is really very similar. This is just, instead of O18, instead of looking at the O18-O16 ratio, this is looking at the ratio of deuterium to hydrogen, deuterium being the heavy isotope of hydrogen that instead of just being a proton, actually has a proton and a neutron, so it's mass 2. And so just like the delta O18 is the normalized ratio of oxygen 18 to 16 in a sample relative to a standard, similarly, the delta D is just the D to H ratio in a sample divided by the D to H ratio in a standard minus 1, and then of course times 1,000 because it's in per mil or parts per thousand. The deuterium, in terms of its relationship to temperature, works exactly the same as the delta O18 and strongly correlates with temperature just like the delta O18 and can be used as a thermometer the same way that Dansgaard showed you could use the delta O18 of precipitation as well.